This is lecture 15. So we are now making a switch and we are jumping to the next main topic, the second main topic of this course, which is process management. Process management. And these slides that I'm showing here are in the course directory called capital P presentation hyphen 2, not 1, but 2.pdf. So we are going to discuss these common PDF slides first, and then we are going to branch off to more up-to-date modern topics in terms of scheduling and so on. So that's going to be our plan here. Let's go into the slides. What is a process? We know that this is a running program. We have seen some aspects of it already. It says here that it's an abstraction known only to an OS. This is not precise, so we can say that it's an abstraction known principally to an OS. But in modern hardware, the hardware itself has knowledge about threads, about processes at the hardware level. So this kind of a strict line is not true anymore, but it is okay to say that it's an abstraction known principally by an operating system, and that's how we will interpret this. All computation must be done by process. So this is a fundamental OS design principle that we will follow here. It is a principle that's also followed by other operating systems like Linux, Windows. Here, just to remind you, in the case of Xenu, but this holds for Linux and Windows as well, we are doing bootloading at the start, bootloader runs, and then at some point we are branching off to Xenu code, in particular code inside this file start.S, which is part of Xenu, where it does some initialization, then it makes a jump to this function null user in the file initialize.c, and you got some sense of these steps by looking into the Xenu code in lab 1, and then from here on, of course, the rest follows. And so this was the boundary here between the bootloading step and Xenu, and I mentioned some of the steps that are done here versus the rest. Here what I'm going to emphasize is that at some point in the code of null user, this guy here, we notice that it sets up this important kernel data structure called a process table, and it inserts an entry for the first entry, 0th entry, and calls itself process with PID, with process ID 0. And we said that it is this guy who custom crafts itself. And process 0, which is now running this code, is the only one who, at the moment that it puts an entry into this process table with index 0, hence PID 0, is a process being created in a custom fashion. It is being handcrafted, so to say. All other processes subsequently, 1, 2, 3, etc., they are all created using the system called create. And this situation happens the same way in Linux, Windows, etc. Also the same way in Xenu and Linux and Windows is that until that moment in this code, which calls other functions of course, but until such moment that it creates this entry inside this process table that has been allocated with entry 0, Hence, there is now a process 0 that exists. Prior to that, there is no notion of a process. It's just code. It's just a sequence of instructions with jumps that are executed by the CPU using fetch, decode, execute, as we know. But till that moment, so from the very beginning when the system is powered on until this moment, there is no notion of a process. No notion of process. It's just executing code. But from here on, when this process table is set up and then the first entry is created, which means this code now, this function, which is a function, is now being run under the name of an existing process called process number 0, PID0. And subsequent to this moment, so from here onward, all instructions, so this is all instructions, all code, are executed by someone. By someone, we mean by a process, by some process. So from this moment onward, all code, just no matter what that code is, it could be app code, it could be interrupt handling code, it could be system call code, someone executes it. That is, a process is the one that is executing that code. And this is what this slide is pointing out, that all computation from this moment onwards must be done by a process. Not like here, where there's no notion of a process, or perhaps there is a notion of a process, but code is being done just by executing it, but not by anyone. No. Any piece of code can be assigned, can be specified as having been executed or being executed by this or that process. That's the assumption here. And to make this happen, of course, we must ensure that at any moment in time on our CPU, there's always a process that's running. Because if there's no process that's running, then if the CPU fetches and decodes and executes some instruction, then it's not being run by a process, obviously. So to make this work, we ensure that there's always a process running on our Galileo backend, and that is our null process. This guy, the guy with PID0, who sets up the kernel principally and then enters into this infinite while loop, as you see inside the code of null user. So at the very end, it's an infinite while loop. And this process has priority 0, as you saw. So this guy has priority 0. You saw that in lab 1. You even modified it to -1. But the important property of whatever value of priority this guy takes is that it must be strictly smallest of all processes. So there cannot be any other process who has equal priority or lower priority. They must all have a strictly bigger priority. And as we said, in a kernel, and that doesn't apply just to Xeno, same for Windows and Linux, a scheduler, that's the part of the OS that we will discuss, it chooses, if it has the option to do so, a process to run which has the highest priority. And there may be a tie, there may be two or more with the highest priority, but it is one of those that's going to be chosen to run, who needs a CPU, who are ready. If a process has a high priority but it's sleeping, then it doesn't need the CPU. So we are only talking about those processes who exist now, who are ready, meaning they want to get CPU cycles, not those who are sleeping, who are waiting on some packet to arrive from a server, but till that packet comes in, they have nothing to do. Those guys are not ready. So among those that really want to use the CPU, in our case, one CPU, the OS, the kernel, is going to pick one who has the highest priority. That's the fixed rule. And then on top of that, we will see how we implement modern schedulers in Linux, Windows, etc., based upon how we are currently doing it in Xeno. And we must ensure that when this is carried out, we always pick a process with the highest priority. We never pick this null process because it's there only to be run if there are no other processes needing the CPU. If there are no other ready processes, yes, then we pick this null process, this process with PID 0 to run. Why? For this reason, all computation must be done by a process. Must enforce it. So, to be a bit more specific and tie this back together with what we've already discussed, let's see. So, let's draw our stack here. Not our stack, but our software stack. So this is the user mode part, kernel mode part. And there may exist a bunch of processes, but they're all not ready. They're sleeping, they're waiting on something to happen, but until that happens, they don't need the CPU. But there's one among these guys, and I'll show it as black here, which is our null process. This is for Xeno null process called in Xeno, or more generically called an idle process, say for Linux and Windows. Plays the same role in this setting. So if none of these guys need the CPU right now, then this guy is there to run. But why do we need to run it to satisfy that property? No one is going to make a system call. Because to make a system call, these guys must be running, because a system call, as we saw, is a wrapper function which has internally a trap instruction that does the trap. But someone needs to run that system call API, that is the system call wrapper function. But by definition, by this setup, they are all not running because they don't need the CPU right now. Perhaps later, but not right now. So therefore, this will not happen because by definition of the setup. But what else can happen? Interrupts, of course, can happen. And the kernel we viewed as being subdivided into two major subsystems. The upper half that responds to the system calls, and the lower half that responds to interrupts. That's our current view. We are going to make it more and more complex as we go along. But this is so far our view. But we also mentioned that when interrupts occur, till such time when we are going to relax that assumption, we are going to assume that whoever is running now, we are going to service, we are going to execute whatever the interrupt handling code here is for a clock, whatever the case may be, as this process. We said we are going to do context borrowing as our strategy. And that's the only strategy that's used by Xeno It's the default strategy that's used by modern kernels, but there's another approach that we will discuss later on under device management. So that comes after memory management. So there we will see another way of doing this besides context borrowing. But at this junction, we are going to, by default, assume an interrupt occurs. There's some process running. If no other processes are ready, it's this null process in Xeno that runs, or this idle process that runs here in the case of Linux and Windows. And we are going to temporarily cease running its instructions and branch to this code. And that's what we are doing in lab 2 through this IDT, interrupt descriptor table in x86, which I mentioned is generically in computer architecture also referred to as an interrupt vector. But we're using terms specific now for our platform. But this is very, very generic overall speaking in terms of design. And through a function pointer that's installed here, you now know that the hardware jumps to this code, which it executes. So it's going to execute this piece of code. But it's not executing this piece of code just nilly-willy. It's executing this code as this process whose context, whose state we are borrowing. So if there are no other processes who are ready, and for that reason we are running this null process with PID 0, same for here, then we are going to temporarily cease running this guy's code, which is just an infinite while loop, and jump to this code and run these instructions, execute these instructions as process 0. If some other process were running here, so it's not this guy that's running, but this guy was occupying the CPU, suppose its PID is PID 30,000, then we would be temporarily ceasing to run its next instruction to, through IDT, jump to the correct kernel code and then run the lower half code of this kernel. As who? As PID 30,000. That's called context borrowing. And that's going to be the default assumption until later when we talk about device management in more detail. So, to make sure that subsequent to boot loading and our kernel setup, where we create this first process with PID 0, and subsequently all code must be run by someone, must be executed by someone, by a process. To make this hold, we are having this process with PID 0 who has the strictly lowest priority by the rule of who we pick next to execute, the one with the highest priority, or a process if there are ties with the highest priority. So this is the underlying setup that ties back together with what we've done, where you have system calls top down and interrupts bottom up. And when interrupts occur, we still need someone to be running. And if there's no one ready to run, the null process here, this guy, must still be running on the CPU so that the interrupt code can be executed by someone. By who? By PID number 0. So with that in mind, let's go back to the slides here. So this fundamental principle behind the scenes has these parts that underlie what this means, as I just mentioned. Just one more point here is that this is a basic generic OS design. there are further optimizations that will be done, and I mentioned one just earlier, but there are other things like issues about power consumption. So for example, if you have a laptop or you have a smartphone, then obviously battery power is very important. And you don't want to consume your battery too quickly. So you want to conserve energy. And so you don't want to, if you can avoid, just run something on the CPU. So make the CPU continually engage in fetch, decode, execute, because this consumes energy. It consumes less energy if it doesn't do that, and it hibernates in some state. And there are different ways of the CPU that's in this limbo state to hibernate. And we're not going to go into those different hardware states here, but there are these optimizations that are done in real world environments today, mobile, like our smartphones, but even in the case of computers that have actually a power line input, so they're connected to a power supply, and so they're not battery powered. So you have a big server farm somewhere, part of a cloud computing server system, lots of servers. Even here, such optimizations that we are here not discussing are implemented. For what reason? Because of heat generation. So all of these computing activities, fetch, decode, execute, they have a byproduct, which is heat. And as you know, heat is a big problem, and it's the enemy of systems, of computing systems. Something is likely to go wrong if a system operates outside of its target temperature range. And so having the temperature of these computing systems, which are not battery powered, they are plugged in, but making sure that there's a sufficiently capable cooling system that keeps a lid on how hot this environment can be is super important, even in systems not powered by batteries. And so therefore, all these optimizations that are on top of what we're discussing carried out are very, very important in practice. We just don't have time to go into all of these advanced topics just because we have only so many weeks during the semester to cover the fundamentals. And there are more important fundamentals than these things that we need to cover, and that's the only reason why we are not going to discuss further on such on such issues as managing heat. But just keep in mind that this is not the entire story. So let's go to the next slide. Process terminology, job, task, etc. We are just not going to use these things here. Switch back to here. But we will talk about heavyweight and lightweight processes. And when we say thread, it's a different name for something that we call a lightweight process. So we need to define what a heavyweight process and what a lightweight process is. So let's see. The best way is to look at this picture and then we go back to the slides. So here are two heavyweight processes. So this is a heavyweight process in this cartoon picture, and this is a heavyweight process. So both are depicted as heavyweight processes. Heavyweight. There are two of them. Inside this heavyweight process, process 1, there are three lightweight processes. This guy, this guy, and this guy. So there are three lightweight processes. And these guys are all part of the same heavyweight process. So it's a two-level hierarchy. A heavyweight process may have one or more lightweight processes. This guy, which is a heavyweight process called 2, has only one lightweight process. So there's a simple one-to-one correspondence here. Here there are 3 to 1. So this guy is like a container. Again, a term that we use a lot for this or that purpose, within which we hold 3 lightweight processes. Here it happens to be one lightweight process. Now, these lightweight processes are often called just threads. And we will sometimes just use them as threads, but to be perfectly clear, it's easier, or it makes it more transparent, to call them by this longer name: heavyweight, and in this case lightweight processes. So what's the big difference here? In this case, these 3 lightweight processes, they are shown to share all data, be it initialized data, be it heap, whatever the case may be. It's shown to share data and share code. The only thing they are not sharing is their stacks. So this thread has its own stack, this thread has its own stack, this lightweight process has its own stack, because we discussed that in typical settings where code is written as function calls, which is common practice today, doesn't mean that that's the only way that we code software, but common way of coding software, including kernel software, is to code software as a bunch of function calls. And for function calls, we need to manage caller-callee interaction, which is what you have been practicing in lab 1 and 2. And in this setting, we are using a runtime stack as our primary means to perform the necessary bookkeeping to make this work. And so every process which is running code, which is likely by default something that's coded using function calls as the means to write code, needs its own stack to perform all of this bookkeeping. That's why this is considered in modern settings, not in all settings, but in many settings, as a minimum requirement for a process to have as its own, that is, its own runtime stack. If a process is not coded by which it performs function calls, even this is not needed. But in general, we assume that that's how modern software is implemented. And hence, in this picture, each lightweight process has its own runtime stack, but otherwise all else is shared. And this is intentional. This is shared because it's viewed as being good. These 3 threads, these 3 lightweight processes are part of the same heavyweight process, which is running typically some app code. It's an app. And to code this app, the app programmer is using 3 threads, 3 lightweight processes that are part of the same app. That is, they're part of the same heavyweight process, which shares data, which shares code, so that this app is efficient and typically will run fast. That's how the app designer uses what we generically call multi-threading coding. So you have multiple threads to implement an application. And typically you do this as multiple processes, that is, this lightweight processes or threads, but they are related because they're all part of the same app. And it's easier, it's faster for the app to run if they share a bunch of data and a bunch of code. So this way of looking at it is intentional and it's beneficial. In this case, just one process that's running. Just one lightweight process is enough. There don't need to be any siblings here, and then that's what you have. But if you look at this picture carefully, this one process that's comprised of multiple threads, each having their own runtime stack, but otherwise everything else is shared. This should remind you of another picture, which is, here is the last slide of the presentation -1 PDF slide that we discussed, and I pointed out this picture shown there, where this is how Xenu's binary executable that you're cross-compiling on the front ends and then downloading on a backend and executing. This is its logical structure: code, data, but one stack per process. This is what Xenu looks like. But what does this remind you of? It reminds us of this picture. Everything is shared. The only thing that's not shared is one stack per thread. So another way that you can kind of relate Xenu to something that's already out there is that you can view Xenu, the whole Xenu system, as one heavyweight process, like so. Of course, we don't call it a heavyweight process, it's called Xenu. And there are no other heavyweight processes, it's the only guy. And then these guys we call a Xenu process that are created using create system call. And otherwise, they all share things. And oftentimes, these kind of models are followed by traditional embedded systems. But these things have evolved a lot, and so some that are used today, they still insist on implementing isolation protection because it's essential to have a reliable system. But if this is what you want, then this is what you can get by implementing a heavyweight process with multiple lightweight processes or threads that otherwise share everything else. That's the good thing. The bad is, if anything goes wrong with this process that's using this stack, this entire thing, of course, gets corrupted, aka it will crash, because there's no isolation protection. Of course, this here is intentional, so this is good. The damage, if this happened, is limited to this one application process, app process P1. This guy is not impacted. This guy is shielded from the ongoings of this guy through this sandbox, through this firewall that we discussed in our first main topic of the course. So it doesn't spread to this guy. We're able to box it in here. This guy's just happily going about its business. The kernel is protected because, again, by the same sandbox. But for an app programmer, we want the app programmer to be able to utilize all of the sharing because it's desirable in some contexts. And in this multi-threaded programs that are running as one heavyweight process that's comprised of multiple lightweight processes, that is exactly what this process model supports. So keep this picture in mind. Is this the whole story? No, there are more complications that we are not going to go into the slides, but I will just mention one of them, which is when you have today's operating systems and apps, sometimes So here is again our picture. User mode, kernel mode, and you have a bunch of processes. And to create a process, we have to make a system call like fork in Unix Windows, create process in fork in Linux, Unix, create process in Windows, and of course create in Xeno. So different system calls that trap down and then perform the act of process creation so that this process becomes the parent who then forks a child. So parent process creates a child process. So this is the way that our things are done through system calls. But there are other process models where this multi-threading idea, where you have one heavyweight process, so this P1 guy, which has three lightweight processes, call them L1, L2, L3. These are the three lightweight processes in the previous picture that otherwise share code data but have their own runtime stacks. This need not be implemented like what I just said earlier. It can be implemented entirely in user mode, in user space. We sometimes call this thing user land. You see these kind of terms being used, which means that when you fork a child, you don't fork a child by making a system call. Instead, in user mode, you create your own process table, which is your own data structure that resides in your own memory. You don't use fork, you don't use create process. Of course, in Xeno, everything is shared to begin with, but let's talk about Linux or Windows. In such an environment, the notion of a process you can implement entirely in user mode, and you keep track of your own processes. So you fork a process, so here is your parent, here is your child. But it's your own abstraction. This is something that exists in user mode. For the OS, for the kernel, it thinks that these are actually the same process. So it thinks, oh, there's only one process. But internally, you maintain your own process table, your own separate PIDs. These PIDs may have nothing to do with the PIDs here, wherein you implement a process being a child of another process, and then this guy doing something, this guy doing something else. Now, why would you ever do that? One benefit of that is you don't have to make system calls. And in lab 2, you get to experience some of the overhead that comes into play when making a system call. And a system call, in general, has much more overhead than a regular function call. So from the overhead viewpoint, this guy is slower than this guy. So if you can create software that minimizes the number of system calls and you're able to stay in user mode and not seek the help of the OS, but carry it out, that will in general result in better, nimble, faster app code. And for that reason, there's a tradition of multi-threading packages, software packages, that are done in user mode, and you create child, parent, all under here. And the kernel, the OS, is oblivious to all of these ongoings. It doesn't know about it. How this is exactly done, what are the technical issues, that's what we don't have time here to discuss. But just note that there are more complicated process models where you can do some other interesting things for different reasons, in this case, performance. One drawback, however, of this model that I will mention, otherwise we would do it all the time, is on modern computing systems where you have multiple CPUs called cores. So you have CPU 0, core 0, and say you have CPU 1, core 1. Suppose that this guy forks a child, and suppose this guy could run on this CPU, or it would benefit, and this guy could at the same time, it could simultaneously, it could concurrently run on this CPU, and we would achieve what we call in computer science a speed up. Because this guy runs at the same time as this guy, you will be able to run them faster together than if you had to run this guy first, then this guy, then this guy. Obviously, that's called speed up. Speed up is typically not by a factor of 2 because you are now running them on 2 CPUs. That would be really the best case in the real world apps. If you get a speed up 1.5 or somewhere between 1 and 1.5 or any range, it depends upon the application domain, then that's much more typical. But it will still be faster than if you could just run it on one CPU, say. But in this way of implementing multi-threading, where you're creating your threads entirely in user space, in user mode, where the kernel is oblivious to the fact that your app is actually acting as a two-threaded process, it cannot utilize the fact that there are two CPUs because these CPUs are governed and scheduled by the operating system, by this guy. And for this guy to utilize both of them at the same time, it needs two threads, two kernel threads, two kernel processes downstairs so that this guy goes here and this guy goes here. But these two guys don't exist separately for the kernel. The kernel doesn't know about the fact that this guy is playing these tricks. For the kernel, all of this guy is just still one kernel thread, one kernel process. And so this potential of making the app run faster by having this part be this kernel thread, this guy be another kernel thread, and then having the OS schedule or run this guy on this CPU and this guy on this CPU, that potential, that opportunity is lost if you do it in this way alone. And so there are, in most cases, always benefits, pros, and cons, and one has to consider in what scenario what may outweigh the other and then make those decisions. So this is so much about process models, but we will stick with what is here in the slides, which is this picture of a two-level hierarchy of a heavyweight process and a bunch of lightweight processes, all of whom share data and text in general. So task thread, lightweight process, maintaining processes. So it's principally known to OS, but hardware has dependence on a notion of thread in today's architectures. They are created dynamically, we all know that, and a key data structure of the kernel is this process table that we discussed. One other term that you will come across often is that you will find the term process control block, PCB. Process control block being used a lot in the context of different kernels. For us, this is the simple and straightforward way to relate it to what we are emphasizing, which is this process table. So this process table is a kernel table, kernel data structure comprised of rows, one for each process that's created here. So this is process 0, process 1, process 2. If this is a heavyweight process, then it will have multiple threads. How that's then kept track of, that depends. Here we are first and primarily focused on the notion of a heavyweight process, within which, of course, there can be multiple lightweight processes, and that can be contained here. But the point is, each entry here we will view as a process control block. So each row, one per process, is also called process control block. Further, typical things that we keep in each entry, in each row of a process table, that is in each PCB, is that it has a PID. It may have an owner. So in Xeno, it is not a multi-user OS, but Linux certainly is. So there's a user name, a user ID, other information that we have to record. What is its scheduling priority? What we discussed. Where are things located? Where? Status of computation, for example. We noted the eFlex register that you will be using a bunch in x86. So this is one of the statuses of what's going on, the flags, the bits contained therein, the program counter, obviously, and other register values. So these are some typical fields or items inside each PCB or each row of a process table. And then if it has, of course, multiple threads, then you have more layering going on with, again, similar information. And that's not all. I mean, I'll say a couple of more things to bring you more up to date on today's operating systems. So let's take, say, Linux as an example. So if you use Linux, then today's Linux operating systems, they have more fancy features than what we are going to discuss in this course. I'll just point out one such thing. It's called a C group. C means control group. So what is a C group? A C group is another abstraction beyond what we are discussing here in the slides, where a bunch of processes are grouped. They are forming a group called a control group. For what purpose? You want these three processes to have certain limitations on the resources they can take up. For example, CPU cycles. What should be their share of the total CPU time? Maybe that share should never exceed 5%. Now, where you get that from, that's a separate matter. But suppose that there's an environment where it makes sense for the software as part of the OS to say, hey, these guys, these three guys, which are part of the same application, they should collectively not get more than 5% of the CPU or disk space. These three guys should not get more than, say, 1 gigabyte of space on the disk or such. So there are other purposes of aggregating processes. In this case, they might be heavyweight processes into groups such that in this example, and that's the case for what is called C group in Linux, you are essentially putting boundaries on the resources that they can utilize, which is you are actually sandboxing resources. So you're splitting up resources and you're saying this much belongs to this group, this much belongs to that group, and that is going to be it. Or we call this more generally resource virtualization. So each of these groups gets a particular share. How that is determined, that's a separate matter. But once that's determined, then the OS makes sure that that policy of this guy not getting as a whole more than 5% of the CPU or consuming more disk space than 1 gig, that's preserved by the actions, by the management of the OS. So beyond this heavyweight, lightweight, etc., there are other mechanisms that are being used today that are relevant. To understand this, what we are discussing now is critical to understand. Then this stuff is not that difficult to comprehend because these are just further extensions. They're just further optimizations in a way, they're extensions. So to be able to extend, you need to know what it is, of course, going to extend from. It makes little sense to talk about this stuff without not knowing what this stuff is. And we are focused on understanding the basic framework under which all of these myriad extensions, of which there are now very many, exist. But underlying all of this is the critical thing that you need to get a good technical grasp of. And then all these myriad extensions, those then can be in most cases very straightforwardly understood. So keep that caveat here in mind. Let's see. Xenu process model, we just said, very simple. Everything is shared except for a per process stack. That's it. Good and bad. Some of the fields of an entry in the process table is, so here it's always a prefix with a PR for process. So state is a process now running on the CPU. We call that thing current. What else have we seen? It's not running on the CPU, but it wants the CPU. We call it ready. It sleeps. We make a sleep system call and it's sleeping. In Xenu, sleep MS is a system call where through the system call we say, hey, put me, that is, this is a process, put me to sleep for this many milliseconds. So if we put here 500, it means half a second. Let me sleep for half a second. There's another call in Xenu called sleep, which is in units of seconds. So this is in milliseconds, and this is in unit of seconds. And obviously you can now imagine that this doesn't need to be coded from scratch. This just needs to call this guy by changing the argument value by multiplying it by 1000, basically. So this is, we have not implemented in lab 2 sleep MS as a trap system call, but you could. And if you did, it would mean that this would internally sleep MS. So suppose that this is the true wrapper function now, x sleep MS, which is a true trap system call. Somewhere it would, in the context of lab assignment 2, perform the int instruction with operand 39 to branch, to jump to the system called dispatcher code as part of Xenu. So this itself is a wrapper code, as we said. And these wrapper functions, when we specifically talk about system calls, I'm emphasizing wrapper, which is a very general term, so that you can get a clear picture of what we're talking about. But we call these things system call stubs. So when you see the term, oh, this is a system call stub, It is what we are here referring to as a wrapper function. This is, of course, much more direct. And this guy is a wrapper function then to this wrapper function. And that's very, very common. It's a wrapper that wraps around other wrappers that then is wrapped around by some other wrapper function. And the more wrapper functions you have, the slower your software becomes because they are all embedded system. They are all function calls. And function calls, although they are faster than system calls, they are still slow compared to not making a function call because function call needs all this bookkeeping done on the stack. We just do it because it makes designing more modular and simpler. But we pay a performance penalty for coding software in function calls. So we don't want to lose sight of that because there are some environments where you don't code software using function calls. That's a no-no. In the environment that we are using, we are still sticking with it because the benefits outweigh the costs that come with it. But don't ignore the cost that making lots of function calls, if it can be avoided and the software is still modular and nice, in general, may result in a faster in a faster performance. So current, ready, sleeping. One other thing that we've already seen is we saw that when in Xeno we create a process, we have to resume it because this create returns a PID if it's successful to make it ready. So that means that when a process is created, it's not ready, and you encountered that in lab 1. It's in a suspended state. So already you know at least 4 of the states of a process. It's running on the CPU, it's waiting on the CPU, it's ready to go, it's sleeping, it's suspended. And there are a few more, as we shall see shortly. We have a priority of a process. This field ignore for the moment. It is important, and it has the term stack pointer there, which can be confusing. We will see what the role of this field is. For the moment, just ignore it. Stack base, this is something simple. So here, what we're talking about is, so I'm drawing Xeno again. So this is for Xeno obviously because this is the Xeno process table. So for Xeno the layout is here is code, here is data heap. I just write data generically speaking, and then we have here stack regions per process for process P1, P2, P3. Base means if we're talking about process P3's entry in the process table, its PCB, then this base means its starting address, and the length means its size. And you know from the create system call that one of the arguments is the stack size. That's this length. That's what this thing says. Name is a string to refer to a process. We don't use it in what we're going to discuss. So process state, current, ready, sleeping, suspended, waiting has to do with semaphores. We'll get to that in a few lectures, and also receiving is to send messages. We will get to these two. There are a few more, but of these 6 listed, you know already 4 of them intuitively based upon what we have already encountered. And of course, each one of them we will delve into detail. This is the actual definition in Xeno. So in Xeno, when we're discussing, the ultimate reference is not the slides, not that, it's not the book, it's the code. So it's the Xeno code that we have given you to change, modify, test. That's what is Xeno as you are using it. All of this other stuff is geared toward for you to understand what that piece of software that we are going to work on is and how it's built. All of this is stuff that's aimed at making you understand that piece of software more easily. But ultimately, it's reading the code of that software, which is the authoritative reference. So always keep that in mind. That's the bottom line. So here are some of the numbers that we are using for the different states. And then comes scheduling. So here's a good time to stop. So we'll continue from here in the next lecture.